Hello there, and welcome to a kind of draw my life style thing where I absolutely will not be drawing my life because instead I'm going to draw a little bit of maths, which admittedly is quite a big part of my life, as well as you know, hoist and duck raps. The reason for this existing is I wanted to talk about and share planes, as they are undoubtedly one of the coolest bit of university maths so far, and definitely the most interesting. But oh, no. Not those planes, silly. No, I got you there, that's a bit of a joke. Instead, we're gonna do these. You wanna do the bigger planes, don't you, with engines and so on. I don't think I know enough about those to talk about them really, because I did just say engines and so on. So instead we're going to talk about these, which are, if anything, even cooler. But maybe they aren't, but they're still pretty cool. For those of you who don't know, in maths we describe a plane as anything that is flat. It can be flat, it can be curvy, or it can be a malformed mess that claims it's flat on the inside, but we're not very interested in those. Before we get started with the planes, I need to mention that they can occur in any number of dimensions that is above 1. Flat planes can occur in 2 dimensions, and flat and curvy planes can occur in any number of dimensions that is 3 or above. Today we're going to be mainly talking about 3 dimensions, because I can draw that, and I don't think I can draw 4 dimensions. I definitely can't draw 4 dimensions. Starting with flat planes, for those you need a vector, and you then need another vector. This other vector can go in any direction that is not parallel to the first, as if it does go parallel, then they go in the same direction and you've done a line. That's a line, it's not a plane. That's bad. Once you have 2 vectors that do not go in the exact same direction, you also need a starting point, as this plane could occur at any height, if you will, in the space. As well as being represented parametrically, where you have a starting point and you then have one vector and another, these flat planes can also be represented Cartesianly, which is not a word, but they can be represented in a Cartesian way. You can see here, if we have the parametric equation 021 plus lambda 101 plus mu 210, which means obviously starting point, and you have a certain number of this vector and a certain number of the next vector, you can then represent this Cartesianly, which is still not a word. If you look, you can have the x coordinate for 0 plus lambda plus 2 mu, the y is then 2 plus mu, and the z is 1 plus lambda. You can then use the y and z values to find that lambda is z minus 1 and mu is y minus 2. These 2 values can then be substituted into that x coordinate to get an equation that is just in x, y's and z's, which is pretty neato, as the kids these days definitely don't say. So that's flat planes. If we move on to curvy planes, things get certainly very interesting. Curvy planes are extremely interesting because of how we can differentiate them. If we look at curvy lines in 2D space, you can differentiate them at any point to get a tangential line. That is dead. That's youth speak. Curvy planes though, you don't just differentiate, because you could differentiate in this direction, this one, or any direction. So you can then decide to differentiate just in the x or just in the y direction. This is what we call partial differentiation. You do partial differentiation by treating either x or y as a constant, as if you go straight down this line, the y value won't be changing. If we, for example, look at the curvy plane, which has the equation z, which is the height, equals x plus y times e to the 2xy, you can partially differentiate this with respect to x and with respect to y. If we do this with respect to x using the product rule and other things, we get the equation e to the 2xy is 1 plus 2xy plus 2y squared. That means at any point on the entire plane, you can sub in the x and y coordinates of it and get the gradient of the plane in the x direction. The same can be done with respect to y, leaving you with 2 different gradients of a plane at the same point, but in 2 perpendicular directions. But that's not all, because as we saw with the line, you can find a tangent to it. With the plane though, you can find a tangential other plane. Now that is wow. So, if we have the starting point, which is where we're differentiating from, and substitute in the partial differentiation with respect to x, and then with respect to y, we get an equation for a plane which touches our curvy plane at that point and has the exact same gradient in the x and y direction. That is a tangent, and that is quite verily cool. So I hope you enjoyed this little insight into how planes work, how they, you know, take in fuel and convert it into no, that's still not those planes, that's the same little joke again. But yes, I hope you did enjoy seeing how university maths looks at planes and how they are certainly, in my opinion, more interesting than just lines.